We're now going to consider predictability from randomness, which is to say how a series of random events can actually lead to a highly predictable outcome. And this actually has quite a bit to do with entropy, because we do consider this from the microscopic point of view, where, for example, there are lots of microstates which have an equal probability of existing, and so, for example, which one does exist would be random, and despite that, we can gain a lot of knowledge about the states of systems. So we can make precise and predictive physical laws, even when the underlying behaviour is random and disorganised. And in fact, statistical mechanics is the name of the field which explores how the macroscopic properties, such as temperature and pressure, result from the random motion that we see at a molecular level. And so the throwing of dice is rather a nice way of illustrating random behaviour. So we see what a 10-sided die on the picture here, and you may have all sorts of dice, especially if you're into role-playing. In fact, the approach we're going to take now, because it's so much simpler, is by thinking like we would a simple binary choice, like tossing a coin and getting heads or tails. And of course we can do this using dice. We can say have a 10-sided die like we've got on the picture there. 1 to 5 could signify heads, and the remaining numbers could signify tails. So supposing we rolled 2 of these 10-sided die in this way, so in other words it'd be like tossing 2 coins. How confident would we be of getting 1 head and 1 tail? And so we should say first of all that we are considering each coin toss or each roll of a die to be entirely independent of all of the other events. And so at first glance you might think, well, we could get 2 heads or 2 tails or 1 of each. And actually when we're thinking about it a bit more carefully, of course there's actually 4 ways of doing it. There's the 2 outcomes multiplied by 2. So 2 from the first coin, 2 from the second coin, multiply those together, 4 outcomes, and this is because there are 2 ways of getting 1 of each. We could get heads then tails, or tails then heads. And so, in other words, with 2 coin tosses, there'd be a 50% chance of getting 1 of each. 2 out of 4 of the possible outcomes. And so, if we're looking at multiple rolls in a more general sense, ultimately we can multiply out brackets this way. And so one way I like to think of it, you could have H representing heads, T representing tails, and if you multiply out that bracket 4 times, this effectively looks at all the different combinations. So this is the H plus T written out 4 times, and then simply multiplying those out, we find these different powers of H's and T's in there. And so again, with 4 rolls, it's 2 times 2 times 2 times 2, that's 2 to the power 4, 16 possible outcomes. And you can see here that it's actually these numbers in front of the H and T terms which are counting up all the possibilities. So you can see here that out of the 16 possible outcomes from the 4 coin tosses, getting 4 heads is only 1 possible outcome, whereas there'd be 4 possible outcomes getting 3 heads and 1 tail, because each of the 4 coins could be the 1 tail. Now the curious thing here is that with the 4 coin tosses, the chance of getting 50-50, 2 heads and 2 tails, that you can see we've got a 6 in front of that in the equation, 6h squared t squared. So 6 out of the 16 possible outcomes are half heads, half tails. So 6 out of 16, that's a 38% chance. 38% chance of getting equal heads and tails with 4 coin tosses, but it was 50% with 2 coin tosses. Now with 2 or with 4 coin tosses, it was very simple just to do it by hand, multiplying out the h plus t to the n. But for slightly larger numbers, it's easier just to consult Pascal's triangle. And we've got Pascal's triangle on the screen here. And you can see that on the right hand side that table is giving information about each row. And the way the row number's decided, the row number's actually decided by the second number in, going from the outside, either from the left or from the right. And for that reason, the very top row there with just the 1 in it is called the 0th row, and that way it all lines up, the row number with the second number in. And in fact you can see the way the triangle is put together, each number in the triangle is the sum of the two numbers sitting above it. And so going along the row, say going along the nth row as defined in the table there, are the coefficients in the expansion of h plus t to the n. So for example, if you go to the 4th row, the row beginning 1, 4, then those numbers 1, 4, 6, 4, 1 are the coefficients in the expansion of h plus t to the power 4. And on the far right hand side there, we've got the sum of all the numbers in the row, and this number actually has to be 2 to the power of n, so it's summing together all the possibilities for n tosses of a coin. Now, considering larger numbers of dice, supposing that we had 10 rolls of the dice, or to put it another way, tosses of a coin, how confident could we be of getting 5 heads and 5 tails if we tossed a coin 10 times? Well, this is where Pascal's triangle is going to help us out. And so in fact on that 10th row of the Pascal's triangle, all the numbers will add up to 2 to the power 10, which is 1024, and all the numbers across the row will be the coefficients of all the different powers of h and t. And so looking along there, you see for example it goes 1, then 10, and that'll be because there are 10 ways that you can throw 9 heads and 1 tail, as the 1 tail could be any one of the 10 throws. And so how then do we determine the percentage chance of throwing 5 heads and 5 tails if there were 10 coin tosses? So you might have a quick think, perhaps refer back to Pascal's triangle. I'll give you the answer in a second. Yeah, so in that last problem, if we wanted 5 heads and 5 tails, we would go along the 10th row of the Pascal's triangle and see the number 252 there, and then we'd have to divide that by the total number of possible throws, which would be 2 to the power 10, which is 1024. And so when you divide that 252 by 1024, that's giving you about 25%. It's only a 25% chance then that you throw 5 heads and 5 tails if you toss a coin 10 times. And so thinking about these larger number of throws, or this larger number of dice, then it would be quite handy to have a formula, especially if we go off the bottom of Pascal's triangle. And so we have this combinatorics formula here. So if we have n throws, then we'll have n factorial on the numerator, divided by, so that's all the possible combinations, and then divided by h factorial and n minus h factorial, h being the number of heads, so the h factorial, basically that's the number of ways you can order all the heads, n minus h, the number of throws minus the number of heads, that'll be the number of tails, a tails factorial, that'll be the number of ways you can order all the tails. So that fraction will give you the number of ways that you can throw h heads from n throws. And so just in case you've not met this idea before, that exclamation mark that I'm referring to as factorial, that means you multiply up all the integers starting from 1 up to that integer there. So 3 factorial is 1 times 2 times 3 equals 6. And so if we're interested in the probability of throwing half heads and half tails for the total number of throws, that's going to be n factorial divided by n over 2 factorial times n over 2 factorial, so n over 2 factorial all squared. And so this is a formula we can use. And so for example, if we wanted to know what's the chance of throwing 25 heads and 25 tails if you tossed a coin 50 times, obviously 50 has gone off the bottom of our Pascal's triangle, so how do we work it out using that formula? So again, you could give that a bit of thought. I'll tell you in just a second. So for that last question, using our factorials, if we've got 50 coin tosses, that's 50 factorial, and if it's going to be half heads, half tails, we would divide that 50 factorial by 25 factorial, 25 factorial. And that gives us a massive number of possible ways that we can throw 25 heads and 25 tails from 50 coin tosses. But then we have to, if we want to consider the likelihood of that, we've got to divide it by the total number of outcomes, and that's 2 to the power 50. That's another extremely large number. But when you divide the first by the second, very large numbers, what you get is about 11% chance. And that is really quite surprising, because we're getting a pattern here, but it's kind of the opposite pattern to what we might have expected. We would have expected, surely, that the more times you toss the coin, the more likely it is you're going to get half heads, half tails. And we're actually getting the exact opposite. So if you toss the coin twice, it's 50-50. If you toss the coin 4 times, it was 6 out of 16, wasn't it? So that was 38%. If you toss the coin 10 times, that came out at 25% likely. And if you toss the coin 50 times, it's only 11% likely that you get half heads and half tails. So what on earth is going on here? And it turns out that we're looking at this in slightly the wrong way. The significance here, really, it's about throwing approximately equal numbers of heads and tails. This is the really significant thing. So what do we mean by approximately equal number of heads and tails? I mean, for example, supposing you tossed a coin 10 times, then maybe if it's between 40 and 60%, so between 4 and 6 heads, for example, that might be considered approximately equal. And so when we consider these different possibilities, we can use the fact that Pascal's triangle, you might have noticed there, is symmetrical. So for example, if you're looking at the possibility of getting 4 heads and 6 tails, I mean, why should that be any different to getting 6 heads and 4 tails? Because they're just equally likely. And so this can actually save us quite a bit of time, because obviously with the symmetry of it, we'd only have to work out effectively about half of the values. So we can work this out using Pascal's triangle. What's the percentage chance of throwing approximately equal heads and tails from 10 throws and also from 50 throws? So it's going to be slightly more laborious because we've got to consider the different possibilities that are involved. But we'll look at the answer on the next slide. So here we have the solution then. So for 10 throws, using the numbers from Pascal's triangle here, we found that the 4 heads and 6 tails, there were 210 ways of doing that. So it will also be the same for 6 heads and 4 tails, and that's why I've multiplied the 210 by 2. And then there's the 252 ways of throwing 5 heads and 5 tails. And so what I'm doing is I'm adding up all those possible ways of getting approximately equal number of heads and tails. And then I'm dividing that by the total number of possible outcomes, 2 to the power 10, and that comes out as 66% significantly. So that's quite a big jump from 25%. Also more likely now than, say, 2 tosses of a coin, which was 50%. So supposing we move on to 50 throws. Now we haven't got Pascal's triangle in front of us with the 50th row, so we're going to have to use the factorial formula to work this out. So slightly more work involved here. So because it's between 40% and 60%, we've got to consider all of these possible throws. So basically anything between 20 heads and 30 heads out of 50, that's going to be between 40 and 60%. So you can see, looking across the working here on the numerator there, that first number in brackets, 50 factorial over 20 factorial, 30 factorial. So that'll be the number of ways of throwing 20 heads out of 50 coin tosses. And it's multiplied by 2 because that could equally be 20 tails and 30 heads. And then moving along, we're looking at 21 and 29 throws, then 22, 28, etc., 23, 27, 24, 26, and these are all multiplied by 2 because they correspond to either heads or tails. But the last term there, we don't multiply that by 2 because it's just 25 heads and 25 tails. And so adding up all of those will give us a very large number, but then we have to divide it by every possible outcome with 50 coin tosses, and that's 2 to the power 50. So what I've done here is I've just sort of expanded everything out a bit, shown my working, and it all comes out to 88%, interestingly enough. So when you go from 10 throws up to 50 throws, it's getting significantly more likely that you're going to be about half and half heads and tails, where in this case we've defined about as between 40% and 60%. So there we go. When we now define half and half as being approximately half and half, we do find, which is probably what we would have expected, that the more times that you toss a coin, the more likely it is that you're going to be about half and half. Now I thought it'd be quite interesting to consider some really huge numbers of throws. And so we were working with factorial formulas before. Remember you had n factorial on the numerator. Now actually factorials get bigger so quickly that your calculator becomes quite limited. So for example, on my scientific calculator, my scientific calculator can't handle numbers multiplied by 10 to the power of 100. And for that reason, 69 factorial is the largest one I can get on my calculator. So if I wanted to do 70 coin tosses, then my calculator is not going to work for this. But actually there is a cunning way of working with very large factorials. Obviously this problem's been had by many people before, and they've had to think about it. And there's something called Stirling's approximation, which is a nice way of approximating large factorials. And so what you do is you take a log. So if you, this is the natural log, log to the base e. So if you take the log of n factorial, that will approximately equal n ln n minus n plus a half ln 2 pi n. This is Stirling's approximation. I actually came across quite a bizarre derivation of this. So one way of deriving this actually is using the binomial distribution or a Gaussian function and equating it to a Poisson distribution. And that's quite a curious way. You can look that up. That's one way of deriving this expression. And so ultimately we need to find this probability of throwing h heads from n throws. And so you see the same fraction there we've seen before, except we've also got 2 to the power n on the denominator, and this is just dividing the number of ways of throwing the heads and tails by the total number of outcomes. And so what I've done here, every time you see a factorial in the formula, I've simply multiplied it out using Stirling's approximation, except I've obviously had to take the log of the probability, because all of these factorials are getting logged, and I've also logged the 2 to the power n. So that's why the final term there is n ln 2. So if you look through that, I guess you can see each of these factorials getting multiplied out using Stirling's approximation, and we're now completely in the realm of logs. So we're working out the log of the probability. But actually one thing, when you look at that, there's going to be some nice cancellation when you look through here. And so when you go through this, you'll see that all the terms in that expression that don't involve logs actually cancel out. And so we get this slightly simpler looking expression coming out at the end. And this is the one we're going to use in our calculations. So supposing we had 1,000 throws, and we can look at 10,000 throws as well. So obviously this is way too big a number to use the factorials, so we're going to use our Stirling's approximation, and we ask ourselves, what's the chance we get about half and half? Now in actual fact, because when you've got all these throws, if it was between 40 and 60%, for a start, that would mean a lot more terms being added up, and also the probabilities are going to get so close to 100%, it could be a bit of a waste of time. So now what I'm calling about half heads and tails, we're actually going to look at between 49% and 51%. As I say, as we saw the numbers going up quite steeply before, if we were looking at 40 and 60, it's just going to look like 100%. So there we go, that's the expression we derived on the previous page. So now we've got to use these factorials. And so if we're if we're tossing the coin 1,000 times, if it's between 49% and 51%, it means we're looking at the possibility of getting 490 heads, 491 heads, etc., up to say 499 heads. And then actually what we can do is we can just use the same number if it's the number of tails, just looking at it the other way around. And then of course we've got 500 heads in the middle. And so what I've done here actually, because it's a fairly long calculation now, I had to sort of resort to using a spreadsheet. And so what I've done is, for each of these values of heads, I've used the formula in a spreadsheet, and I've worked out ln p using that formula. And you can see here I've got ln p down the side in that column on the table. And so having worked out ln p, if I want to know what the actual probability is, I just need to exponentiate that, to say e to the power of that number. And so on the right hand column I've got the actual probability. So if I want to know the overall chance of getting between 49% and 41%, then all of those probabilities there, these are probabilities between 0 and 1 rather than percentages. For 490 up to 499, I'm going to have to double that and use a sort of symmetrically equal number of tails, and then add on the 500 heads, 500 tails, which is the number at the bottom. And so when I go through all of that, I get the answer of 49%. So that's fairly high, considering that we're just looking at between 49% and 51%. Bear in mind we were looking between 40% and 60% last time. So that's a fairly decent chance of getting pretty close to half heads, half tails, just plus or minus 1%. And then we can do exactly the same thing if we have 10,000 throws. It's just a bit more work this time, because we're going to have to, if it's between 49% and 51%, and we've got 10 times as many throws, we can have 10 times as many calculations to do. So actually, this time, I'm not even going to give you the table, but I did actually use exactly the same method. Of course, on a spreadsheet, it's no work really, just to make some extra rows. So we worked it all out in the spreadsheet, and this time it came to 96%. So we're up in the realms of very high probability now. So once you throw 10,000 times, you've got a 96% chance that you're going to be very close to half heads, half tails, like plus or minus 1%, as you can see there. And so here we see how these percentages have grown. So from 10 throws, you had a 66% chance, it was between 40 and 60%. And then we're up to a 96% chance, it's between 49 and 51% with 10,000 throws. So that's like a massive increase in likelihood that you're getting very, very close to 50-50 being observed. And so going up and up like we are, it seems like we're looking at really big numbers. But actually it's going to get much bigger still. And so one thing I did was then magnified up to 1,000,000 throws. And again, you know, you can do this on a spreadsheet. It's getting a very large page on the spreadsheet, but you can still do it. And what you find then is, again, you can get a high level of chance, a 95% chance you're going to get very close to 50-50. But in the case of 1,000,000 throws, this is the chance it's going to be between 49.9% and 50.1%. So it really is going to be very close to 50-50 once you get up to 1,000,000 throws. And so, as I said, we're going to be looking at some super large numbers. And of course, despite 1,000,000 seeming large, when you start looking at in the context of numbers of molecules in a kind of macroscopic scale, 1,000,000 doesn't even scratch the surface. And so let's think about how many molecules of water would you get in a glass of water? We can quite easily work this out. We've got relative molecular mass of 18 in water. We know the density is 1. We know the Avogadro constant, 6 times 10 to the 23. So a little calculation for you. You can calculate the number of molecules of water in a good sized glass, 300 cm cubed. Quite a simple calculation. And it gives you a nice round number as well, actually. So you could pause for a second or hang on, I'll just tell you the answer. There you go. So it comes out as 10 to the 25 very nice round number, a gigantic number, dwarfs 1,000,000. And so this is the number of molecules that we've got just in this glass of water. And in fact, it's such a mind-bogglingly big number, this. It turns out that number is a lot bigger than the volume of water in all the oceans measured in units of these glasses of water. And so you hear these, don't you, with Avogadro's number. I mean, one classic one you might have heard is that, if you take a glass of water and tip it in the ocean, and then if the oceans were perfectly mixed up, and then, you went to New Zealand, got the same glass, went to the beach, filled it up with water from the sea, the question would be, how many molecules of water from the original glass are in that glass? And of course people just assume there's going to be no molecules of water, and it turns out there's thousands of molecules of water, and it's because of these mind-boggling numbers that we've got here. So again, this business about predictability from randomness, doing a few more of these examples. So I'm just throwing another one in here. Supposing we did 100 throws, a similar calculation to what we did before, shows there's a 90%, 97% probability that you're going to be in that 40 to 60% range. And so what I've done is I've actually collected together all of these scenarios where we see this high likelihood, and we're talking about numbers like 95, 96, 97% chances of finding the proportion of heads and tails. And so here we are, and we can see there's actually a bit of a pattern emerging. So numbers of throws, we've got 100, 10,000 and 1,000,000. And so we can see this is quite neatly ordered up there in terms of powers of 10, going up 2 at a time. And so then there's the likely deviation from 50% heads. So what that's saying is, so you can see this percentage deviation, this is changing in a regular way, 10, 1, 0.1, so it's changing by a power of 10 each time. And so what this is saying is that if you toss a coin 100 times, 10 to the 2 times, then it's 95 to 97% likely that you'll get 50% heads given a 10% deviation from that, so between 40 and 60. That's what the top row tells us. Then the second row tells us is that when you get to 10,000 tosses of coins, then you're looking again at a 95 to 97% chance that you're going to get half and half heads and tails, but this time within a 1% tolerance, so between 49% and 51%. And then likewise the bottom row tells us that for 1,000,000 throws, 10 to the 6th throws, you're 95 to 97% likely to get half heads, half tails, but within a tolerance of 0.1%. So you're 95 to 97% likely to get between 49.9% and 50.1% heads and tails. So there seems to be it's so neat, that table. It does seem to be there's some sort of pattern going on, something regular happening. So it seems to be hinting that by increasing the number of throws by 2 powers of 10 decreases the likely deviation from 50% heads by 1 power of 10. And this is something that actually we'll be able to explore in a moment. And so, yeah, what does this imply about predicting molecular properties? Well, let's have a think. So we can do a kind of thought experiment here. So with our glass of water, we had 10 to the power of 25 molecules. So a bit like tossing a coin, supposing there were 2 possible states of the water molecule, state A and state B, and there was a 50% chance, completely randomly, that a molecule was state A or state B. So it's just like tossing a coin, in other words. Then if you were to make measurements on the water molecules, how much deviation would you get if you were measuring whether it was state A or state B? It's the same type of problem. We're just considering the molecules to be like coin tosses. So there's the table we had up there a moment ago. And so we're going to ask ourselves, what are we likely to see? Well, we've got 10 to the power of 25 molecules here. But actually, when we look at the numbers of throws, which is a bit like numbers of molecules, all those values are actually even numbers. So supposing we just underestimate a bit for now the number of molecules, let's say it's 10 to the 24 rather than 10 to the 25, then you can see that each time we step up from 10 to the power 6 by a couple of powers, then our percentage deviation goes down by a factor of 10. So you can see if you're going to step from 10 to the 6th up to 10 to the 24, how many steps is that? That's 9 steps of 2 powers, isn't it? 9 steps of 2 powers. So that means we go another 9 steps down from 0.1%. So the percentage deviation, that's going to be 10 to the power minus 10%, isn't it? So that's an absolutely tiny deviation. And so 10 to the power minus 10, that's smaller than a billionth of a percent, which would be 10 to the power minus 9. So it's actually, a tenth of a billionth. And so this is like 1 in a trillion, because to convert a percentage chance into a 1 in something chance, you're going to have to multiply by 100. So this is 1 in a trillion, and actually this is actually us having rounded down our 10 to the 25 to the nearest even number power. So it's even a smaller deviation than that. And the curious thing about this is that we wouldn't be able to measure it, because if it's going to be 50-50 and the deviation is going to be something like 1 in a trillion or even less than that, that is such a tiny difference from 50-50, your measuring device wouldn't be able to measure it. So for example, you could have a measuring device with 10 significant figures, which is just a crazy number of sig figs. I mean, you never have 10 significant figure measuring devices in chemistry. And yet that wouldn't pick up a 1 in a trillion. I mean, a trillion is 10 to the power 12, isn't it? You wouldn't pick up a 1 in 10 to the power 12 difference if you only had 10 significant figures. So it just goes to show that actually no measuring device would be able to observe that deviation. So this is what I mean by predictability from randomness. Even though there's just a completely random chance whether an individual molecule is in state A or state B, that prediction of having 50-50 would be seemingly perfect as far as your measuring device is concerned. So I thought I'd actually go a little bit further than this. I thought it'd be quite interesting. So for example, that table we saw earlier, which kind of hinted at what might be going on with gigantic numbers, like 10 to the power 25. You think about this, when you're using ultimately Pascal's triangle, we're looking at a binomial distribution. And then when you're looking at extremely large n in these cases, you actually end up with a so-called normal distribution or Gaussian distribution. This is your classic bell-shaped curve. And actually we can apply this smooth curve. Obviously Pascal's triangle isn't smooth, it's just integer numbers. But once you get up to colossal numbers, then it, to all intents and purposes, looks smooth when it's plotted as a curve. So this is what we've got in the diagram here. And so you can see the standard normal distribution we can see on the right hand side. And in the standard normal distribution, in all the textbooks, you can see that the mean, mu, is equal to 0. And the standard deviation, sigma, which we've got along the x-axis, is equal to 1. And this way, we've got a formula of a curve here. The formula of this curve is this exponential formula there. So this is our standard formula for a normal distribution. And actually, when it comes to integrating under the curve, which is what we're going to need to do for probabilities, so actually, as I say, it's normalized so that the area under the graph is exactly 1, and that way we can use the area under the graph as a measure of probability. Now it turns out that, slightly bizarrely, you can't actually integrate between limits on this particular function. You can integrate the whole graph, or obviously from 0 to infinity would be the integral will be a half as it's symmetrical, but other than that you can't integrate analytically, you just have to look it up in tables, in so-called statistical tables. And so here, obviously when we're looking at our distributions, the maximum there that we see in the middle, that mean, it's not 0, it's going to be half of the number of the coin tosses. So we're going to be dealing with a slightly different type of curve. So our mean is going to be n over 2, where n is the number of coin tosses, and the variance, which is sigma squared, the square of the standard deviation, by definition this is the number of coin tosses multiplied by the probability of heads multiplied by the probability of tails, and since those are equally likely, this is n over 4. And so it turns out then that if sigma squared is going to equal n over 4, we can say sigma is going to be the square root of that, which will be root n over 2. And so actually what we're going to be able to do is we can take our values effectively from Pascal's triangle, and we can correct for them so that we end up producing the normal distribution as we can see on the screen. And the advantage of making this correction is that we can then look up the integrals, which are the probabilities. And so for this correction, what we're going to do is we're going to take our own values, if you like, the x, and so we're going to subtract our mean, and so that means that ultimately we'll sort of shift it onto that 0 line, and we're going to divide by our sigma, which was our root n over 2. So subtracting our mean, that's subtracting n over 2, and then we're going to divide the whole thing by our sigma, which is root n over 2. And so that's the same thing as multiplying by 2 over root n, the value minus n over 2. And we're going to apply this in the next slide. So here we are, we should be able to work out some probabilities from this for even absolutely vast numbers of throws. And so we're looking for deviations from the mean. So of course the mean is going to be like the 0 line, as you can see on the diagram here. So do you remember, of course, when you're looking at like Pascal's triangle, the 50-50, that was always the largest number in the middle of the row. And, and so here we're going to be looking at deviations from that largest number. And so we've always been thinking about it in terms of the percentage from 50-50. And so since it's a percentage, we really ought to take that d and divide it by 100. So it's, as it were, the pure number. And we're going to have to multiply it by n, the number of throws, to see the absolute amount. And so what we need to do is we need to convert it to the standard form of the normal distribution. So we've got that multiplied by 2 over root n factor in there, and also we need to subtract the n over 2. And so because this deviation is from the 50-50, that 50-50 is the n over 2. And so by having not written n over 2 there, we've subtracted it off. And so what we're going to have to do is we're going to have to solve this integral here, this expression. And so what we're doing then is we're looking at the integral, we're going from minus infinity, which is like the far left, and we're going to go up to this point, which is this 2d over 100 root n. This is having converted from our, as it were, Pascal's triangle into the normal distribution. And so that's going, as I say, from the far left to just a little bit after the 0 line. And then the significance is, if you look at the right hand side of that bracket, we're then going to subtract a half. And so the half, that will be the area under the curve to the left of the 0 line, to the left of that green vertical. So when you subtract the 0.5, all you're left with then is the very small slither after the 0, going to that small percentage deviation after the 50-50. And then this is all multiplied by 2, which is what you see on the far left there, to reflect the fact that the deviation is both sides of the middle, because obviously it could be, it's like 49% heads or 51% heads. So we're looking at the deviation either side of 50. And so we find something very neat actually drops out of this when we consider all these deviations. So you can see here that in the upper limit of the integral, we've got the factor d in there, which is our percentage deviation. And we've also got the n, the number of throws, but the number of throws is square rooted. And that's very significant, because can you see that what we said before was that if you increase the number of throws by 2 orders of magnitude, then the percentage deviation went down by 1 order of magnitude for the same probability. And this is what this is pointing at effectively, because we're square rooting the n and multiplying it by the d effectively. So you can see therefore that if n goes up by 2 orders of magnitude, and if d goes down by 1 order of magnitude, it actually does not affect the value of that limit. That 2d over 100 root n stays the same if n, say, goes up by a factor of 100 and d goes down by a factor of 10. And this is what we did in the table. So it just goes to show that it's no coincidence. It means that that limit is actually the same every time. So it means we're basically looking up the same integral every time. And when you look up in the tables what that integral is, then what you find is that you get 95%. And so this is why we kept finding, this sort of value like 95% coming up. So this is I think rather an sort of elegant mathematical, effectively proof I stumbled across that confirms what was going on in the table there. And so it's just spelt out here on the slide about these steps up of 2 powers of 10 in the throws, causing a result of 1 power of 10 going down in the deviation from 50-50. And so this confirms our earlier approach. So just to finish off, a few questions here to do with predictability from randomness. And so you can perhaps just work out one of the results you were given here to do with 100 throws. Then there's a fairly simple one about molecules of water in a drop. And then finally thinking about 10 to the power 20 coin tosses based on what we were just talking about from that generalizing that table. So a few things for you to think about there.